Welcome to AWS reInvent, session DAT 309, Deep Dive on Amazon Neptune. I'm Brad Beebe, General Manager for the Amazon Neptune service. Graphs are awesome. And the reason that they're awesome is graphs allow you to use the relationships in your data to do new things. Today, we're going to go through what's inside of Amazon Neptune and how it works. We're going to talk about how Neptune stores graph data and evaluates graph queries. We'll provide a few tips for you on building high-performance graph applications. And did I mention that graphs are awesome? The reason that graphs are amazing is that they're all around us. Graphs are a data structure. They consist of nodes and links, or vertices and edges, and they can represent relationships between things. And it turns out that graphs show up in all kinds of important things. So for example, any kind of network, a communication network, a social network, a security network, all of these are well suited for a graph network. But there's also things like biological processes, organizing information that lend themselves to graphs. And so graphs truly are everywhere. The image that you're seeing here is taken from a data set that consists of air routes. So in this data set, airports, represented by the green circles, represent nodes, and routes, scheduled flights between airports, represent the relationships or the edges between them. And it's taken from a data set that was developed by Kelvin Lawrence, who's the author of a book called The Practical Guide to Gremlin. We'll use this as an example later on. Customers ask us, when should I use a graph? Or when should I use a graph database? And the answer is, you should use a graph if you have relationships in your data and you want to ask questions that involve traversing those relationships or expressing patterns over the relationships. In those cases are when you should use a graph. Using a graph to solve these kinds of problems is faster and more effective, and it's much easier to operate. So, what kinds of problems are customers solving with graphs? Customers are building knowledge graphs. Knowledge graphs are a way of organizing and structuring information for better access and understanding. Suppose that you have a couple of different data sets in your organization, or maybe many or hundreds or thousands, and you want to be able to bring them together to help your data science team to process them, or to drive better business outcomes, or to help people search better. A knowledge graph allows you to use a graph structure to link them together and make them easier to access and understand. One of the exciting things that we see in the knowledge graph space and in graphs in general is that customers are starting to think about how graphs and machine learning and AI can be applied. Traditional AI would be applied to attributes or rows and columns that you might have in your relational data. But it turns out that when you take advantage of the relationship information in your graph, and you use ML that's purpose-built for processing graphs, you can get much higher accuracy and better prediction outcomes. So that's a really exciting space. Customers are also building identity graphs. Identity graphs use a graph model to link together different pieces of information that organizations have about customers, devices, or any other kind of entity that you might be interested in. So, for example, imagine that as a business, you have different services. So maybe you have a billing service, maybe you have an accounting service, maybe you have a payment service. And different customers use them, and they use them in different ways. They use them for their mobile device, they use them from their web browser, they use them within a different household. And you want to try and understand, of all these interactions that we're having, who are the actual customers, and how can I know them better? How can I understand what they're using, and who are the sort of people or entities in the real world that are behind it? And an identity graph is a way that you can do that, and you can build that 360-degree view of your customers or your other information. There are lots of different ways to detect fraud. But when you look at fraud on a transaction by transaction basis, looking at each transaction and its attributes, there are only certain kinds of things that you can detect. But when you begin to think about a fraud graph, and you take not just the particular event, the gaming activity, the financial transaction, but then also look at the context of the relationships around it. Who are the other actors that did this? What other accounts or games are they playing? You begin to get a much richer set of information, and you can use that aspect of the fraud graph to detect fraud in new ways. So also a very exciting use case. Thousands of customers today are in production with knowledge graphs, identity graphs, fraud graphs, and many other graph applications and use cases using Amazon Neptune. In the graph space, there's really two major graph models and frameworks. The first is something that's called property graph, or sometimes labeled property graph. And property graphs consist of nodes and edges, and these nodes and edges can have properties on them. The leading open source framework for property graph is something that's called Apache Tinkerpop, and Apache Tinkerpop provides an imperative traversal language that's called Gremlin. There's also other vendor implementations of property graphs, but as of today, there are not any standards around property graphs. So for example, what is the property graph data model? What are the standard ways to query a property graph? There are some activities in place, but by and large, there are no standards associated with it. The other graph framework is something called the Resource Description Framework, or RDF. RDF is a recommendation from the World Wide Web Consortium, or the W3C, and it was originally built to describe resources on the web. RDF expresses graphs in terms of triples, so a subject, a predicate, and an object. Brad is a speaker, that would be a triple. And it uses these triples to build up a graph over time. The way that you query an RDF graph is with another W3C recommendation, which is something that's called Sparkle. Sparkle is a declarative graph query language for RDF. Customers often ask us, which graph model should I use? And there's really, from a technical perspective, you can do almost any use case with either graph model. What we see is that really customers want both. And the reason that they want both is that when you look at your problem and you see there's relationships in your data and you want to ask questions over them, you realize that you want to build a graph application. But that's it. You want to build a graph. You don't think about, do I want to build a property graph? Do I want to build an RDF graph? What are other aspects? And so from our perspective, we want to enable you as a developer, as an application builder, to build a graph and use the framework and the APIs that are best for you. Maybe you want to take advantage of the standardized data interchange formats from RDF. Maybe you want to do semantic alignment using some of the languages and the features found in the semantic web. Maybe you want to use property graph. Maybe your developers find thinking in nodes and node properties and edges and edge properties is more of a natural fit. Maybe you want to use them together. But from our perspective, we see you want to build a graph, and that's really where you want to focus. What's inside of Neptune? The core of Neptune, if you look at the rectangle in the center of your screen, is a purpose-built, high-performance storage engine that's durable in ACID with immediate consistency and optimized for graph queries. That engine itself is exposed through both a property graph interface supporting Apache Tinkerpop and providing a Gremlin WebSocket server, as well as a Gremlin REST endpoint, and also supporting RDF graphs. So we support a Sparkle endpoint, which is exposed as a REST interface by the Neptune interface. And you can use these to build your applications on top of the service. In addition, we support the Neptune workbench. The workbench is a Jupyter notebook-based tool that you can provision either through the AWS console or yourself through the CLI and APIs that provides you a way to connect to your Neptune instance and use the notebook experience to query it, to issue commands to manage it, and to visualize parts of your graph. So it can be a very important tool as an application builder to build graph applications. In addition to the open standards and open source APIs we support, we also provide services around managing and building the application. So for example, we provide a fast, parallel, non-transactional bulk loading service. This is exposed as a REST endpoint, and you post a JSON document to it, where the JSON document contains a specification of the load you'd like to perform. Once you've posted it, the service performs that load for you, and you can check the status of it. We also support a streams interface. The streams interface exposes change data capture records. These change data capture records allow you to track changes as they're going on in the graph. And so if you want to connect your Neptune instance to something else, to Elasticsearch, to another database, you can use the change stream to do that. You can also use it to do things like simulate triggers and take certain actions when things change in your database. So very useful for building applications as part of a larger architecture. In addition, we provide APIs to access and understand the status of your graph. So there's a status API that reports JSON documents containing information about what is the cluster parameters, what is the configuration of your cluster. Those things are accessible there. And then finally, as a builder, you want to make your graph applications run as quickly as possible. And so we provide both Gremlin and Sparkle query explanation and profile tools to allow you to understand your queries, understand how they're going to be executed, and to go back and improve their performance as you need to. Neptune is delivered as a managed service. And as a managed service, it sits on top of a cloud-native storage layer that was originally developed for other instance-based databases on AWS, and this is what's shown at the bottom of your screen. That provides multiple availability zone high availability. It supports encryption at rest with customer-managed keys managed in the AWS Key Management Service, or KMS. It provides continuous backups, snapshotting, cross-region snapshotting, and it also supports some of the compliance regimes that Neptune is already participating in. So, for example, if you want to build an application with HIPAA compliance, Neptune is part of that. If you want to build something with PCI DSS. Let's dive a little deeper into the storage service. When you create a Neptune cluster, in addition to the instances that process queries, you also create a shared storage volume. This shared storage volume is managed by the scale-out storage service, and it grows in 10 gigabyte segments. Each of those segments is stored in 6 copies across 3 availability zones, and that's how the storage service guarantees both high availability and durability. The service itself is not something that you as a customer have to configure and manage. It's all handled through Neptune. But it does things like automatically replace failing storage nodes or do a performance optimization for striping the data on disk. And so the storage service is really underlying a lot of the durability and availability story for the service. Today, the storage service supports segment sizes of up to 64 terabytes, which in our testing translates into graphs of between 100 and 200 billion nodes, edges, and properties. The other role of the storage service is for replicas and high availability. So each Neptune cluster has one instance that's in a role of a primary writer and up to 15 instances that are in the role of read replicas. When you make a write to the primary writer, that write, once committed, is acknowledged by 4 of 6 different nodes in the service layer and then is immediately available on the write master. At that point, the commit point in the storage layer rolls forward, and the read replicas can then read off of the new commit point. Now, the read replicas have repeatable read consistency. You will always get a consistent read from a read replica, but there can be a difference between the latest commit point on the write master and the commit points from the read replicas. That's something that you can monitor with a CloudWatch metric for the replica lag. Typically it's less than 10 milliseconds. And it's something that you should also consider as you think about cluster configurations for very high write throughput. So for example, if you are doing a very write intensive workload, it's important that you have your read replica to be sized of the same instance size as your write master. And the reason is that when you're making writes, you're using CPU and memory resources on the write master. And to be able to apply those writes in a timely manner, the read replica needs to be able to have sufficient resources to be able to keep up. If you have a situation where you have a very large writer and a very small reader, you can end up with in cases where the reader cannot keep up and the system automatically detects that it's falling behind and will cause a restart. Now, the restart isn't really a problem because of the high availability features. What happens with a failure of the master or one of the replicas is that the service will automatically replace it. So for example, if your write master goes down and you have a read replica, the replica will be promoted into the new write master. And typically that failover takes less than 60 seconds. Now, if you have this scenario where you don't have a read replica, the service will automatically provision a new instance for you, and that new instance may take a little bit longer to be available, but nonetheless the service will restore its availability. There's several different ways for you to connect to Gremlin and RDF graphs using Neptune. I've put examples here from open source, and I think the thing to point out is that if you want to use IAM authentication with either Gremlin or Sparkle, we provide open source libraries that do the SIG-v4 signing for you such that you can use your IAM authenticated connections to Amazon Neptune. And I encourage you to take a look at some of these libraries as you're going through building applications. Now let's switch into looking at how we store and query data in Neptune. And we're going to come back to that air routes data set that I showed you on the very first slide. So this is a subset of that. It's looking at a particular sets of routes between Seattle and Frankfurt. Now, if you look at the circles, they represent the nodes. The arrows labeled with routes represent edges that are representing routes. You'll see that the arrows on the end indicates it's a directional edge. All edges in Neptune are directional. And in this case, the code pointing to the airport codes is representing a property on that graph. We don't have to look at the graph as a PowerPoint diagram. You can use the Amazon Neptune workbench to be able to query the graph and provide a visual view in your Jupyter notebook of the graph. And this is an example of another segment of the air routes data shown in the Neptune workbench. Suppose that we want to find out all the airport codes that have a one-stop connection between Seattle and Frankfurt. How would we do that? Well, in Gremlin, we'd execute a traversal that looks something like what you see on the left of your screen. So let's take a quick step through it. The first line is the g.v. This means access the graph object and bring back all of the vertices in the graph. Now we know we want to start with the Seattle airport, so from all the vertices we're just going to select the Seattle vertex, or all vertices that have the code Seattle with this has code SEA. Then we want to step out one hop. So we want to find all of the airports that are one route away from Seattle. And we do that with the out route. Now you'll notice between those two steps we had an as via. That means basically we're going to save those intermediate results off and we're going to provide a virtual label called via on the path traversal. Now that we've got this set of Tokyo, Las Vegas, and Seoul, we want to go through and go out one hop and find which ones of these can access or have a route to Frankfurt. And so again, we do an out. So we do out route from that intermediate set to Frankfurt, and we do that with the same mechanism. So we do the has code fra to be able to do that. Now that we've found these paths, starting from Seattle to Frankfurt, we want to only go back and select the ones that we labeled in the previous step with this via tag. So we do that, and then we return the code, and the last is the values of code. And so that's how we'd answer this question in Tinkerpop and Gremlin. How does this data look on disk? Neptune uses a quad data model to be able to represent its graph information. And the quads consist of a subject, predicate, object, and graph. And so if you look at the table on the right, and you look at the first row, you'll see the subject is 22. That's the node ID. And then you'll see code SEA. So that's basically saying there's a node, which ID 22, that has a property Seattle. And you'll see in this case the graph position is the default. And for nodes and node properties in a property graph in Neptune, that's the value for the graph position. If we move down one line, you'll see that it starts with 22, but the predicate is route. And then rather than having a value in the object position, we have another identifier. And that happens to be the identifier for the Tokyo International Airport, airport code HMD. And then you can see in the graph position, we have an edge ID. And so this is how in Neptune, it represents that we have an edge expressed in the quad. And if you go through the rest of the table, you can see the same kinds of information. Now, we can also ask the same question in Sparkle, but it looks a little bit different. So the first thing that you'll notice, if you look at the left of your screen, is these things that look like URLs. They're actually IRIs, or Internationalized Resource Identifiers. And remember that RDF was built to describe resources on the web, so it uses these concepts of IRIs to help define strong concepts of identity. The prefix mechanism helps to simplify it as you use it and refer to these IRIs within queries and other operations on your graph. Whereas Gremlin is an imperative traversal language, Sparkle is a declarative query language. So if you're familiar with SQL, Sparkle will look somewhat familiar. So let's take a look at this query. The first thing that we see is that a triple pattern that starts with the Seattle airport code. So we see airport colon Seattle, that's the subject position. Then we see edge colon route, so I want to find all the routes. And then we see this question mark via. And that means basically evaluate this triple pattern with the first two values and store the results in a variable called via. The second triple pattern that we see in the Sparkle query this time starts with a variable, and it's a shared variable with the previous one. So start with the variable and then find everything that has edge routes with a destination node of Frankfurt. And so here we've effectively used these two triple patterns with a shared variable to create a join. And in doing that, we've traversed from Seattle into the intermediate nodes, and we've traversed from those intermediate nodes into Frankfurt. But we actually want to return the airport code. So we add a third triple pattern, this question mark via prop code via code, and you'll see that in this case the triple pattern has two variables in it, but the variable via has already been bound by the previous triple patterns. And so we're really just binding the code and getting that to be as return value. So that's how you evaluate that Sparkle query and answer the same question. So let's look at the data model. Again, we have the quad representation. You'll see the prefixes that we talked about. And we look at the first row. It also represents the Seattle node, but you'll see as the subject, rather than having a code or a node ID, we have an IRI, and then you'll also see the rest of it looks very similar. Looking at the next row, you'll see the subject is an IRI. It has the same route as the predicate, but the object value is an IRI. So the object value is pointing to the Tokyo International Airport node. And you'll also notice that the graph position has an IRI too. And that's, in this case, we're using the named graph position of the RDF graph to store edge properties. There are lots of different approaches to do edge properties in RDF, and this is one of them. One of the big challenges that customers have in operating and managing graph databases is managing query performance over time and maintaining indices. Neptune automatically maintains 3 indices over the quad's data layout. There's perfect coverage of a quad's layout, has 16 access paths, and can be accomplished with 6 total indices. But based on the query patterns that we see, we automatically create 3 of them. So the first is called the SPOG index, or the SPOG index, and it consists of a key of the subject, predicate, object, and graph. And this provides very efficient lookup if you have a subject and predicate bound, or subject, predicate, and object. So if I want to find a particular node ID, Seattle with the airport code, that will be an index lookup against the SPOG index. The second index that we maintain is the POGS index, the predicate, object, graph, subject index. And that provides efficient lookup if you have a property value or a property name and a property value bound. So if I want to find all nodes that have the code Frankfurt, that would be an index lookup against the POGS index. The third automatically maintained index is the GIPSO index, the graph, predicate, subject, object index. And that allows you efficient queries where you have the graph or the edge ID bound and the property value. We do have one optional index that you can enable using the cluster parameter groups, and that's the OSGP index. The OSGP index is useful if you have a lot of queries that start only with an object value. So I only want to find the string fra in my graph. Or if you have graphs that have a large number of predicate or distinct property values. So if you have more than 10,000 properties or more than 10,000 unique predicates, this index can be very helpful for you. What if your graph is in a relational database? Or what if your air routes are in a relational database? Well, you can also use the AWS Database Migration Service, or AWS DMS, to be able to take data from your relational database and convert it into a format that can be loaded into either a property graph or your RDF graph. For a property graph, we provide a JSON document in which you can express the mapping from your relational tables into your property graph. For RDF graphs, we support a subset of the W3C R2RML standard that allows you to do mappings from a relational database into your RDF graph. Once you've done that, the DMS service will automatically export that data and initiate a bulk load of it into the Neptune cluster. So if you have graph data or you want to use a relational database in conjunction with your graph, you should check it out. It can be very helpful. We often see customers using Gremlin in high-performance environments. So for example, managing real-time media content or video catalogs. And in those kinds of situations, customers often find that the open source client drivers aren't giving them the performance that they want for either high availability or efficient use of their read replicas. And so we've released a Neptune Gremlin client, which provides a thin wrapper around the open source Gremlin clients. And it uses a combination of lambdas and the status API provided by the Neptune clusters to make your client connections Neptune cluster topology aware. And that means that the client connections are aware of the number of replicas in your cluster, and if the topology of the cluster changes, for example due to a failover event, or because you intentionally scaled the cluster up and down based on anticipated traffic loads, that the clients will automatically make use of those additional resources. So by using this, you can achieve better utilization of your existing read replicas, and you can have a faster failover time in the event of a failover. If you're interested in learning more about Neptune at other reInvent sessions, I've included some other related tracks here. We'd love to hear from you about how you're using a graph or how you'd like to use a graph, how Neptune's working for you, what we can do better, and how we can make it easier for you to build graph applications over the relationships in your data. I want to thank you very much for your time, and I'd really love to hear from you. Thank you.